Today we will continue through the next topic. It is the Heisenberg's uncertainty principle. You already familiar, at least you heard the definition of the Heisenberg uncertainty principle. This is introduced by Werner Heisenberg in the year 1927. This is one of the most celebrated, you can say, the results of quantum mechanics, introduced in the year 1927. He was a German physicist. And here within that is Heisenberg uncertainty principle. The meaning uncertainty means it is not sure. You know the meaning of uncertainty. It means not sure, not certain, or you can say it is not certain. So Heisenberg introduced the principle is called the Heisenberg uncertainty principle. According to this principle, he said that Heisenberg said that one cannot know all the things about a microparticle at the same time. It means you cannot know a complete information of a microparticle at the same time. It means you cannot measure simultaneously all the parameters of observation 100% with 100% certainty. It is not possible. So here see that we are dealing with the quantum mechanics. We are not going with the classical mechanics. Understand? So this quantum mechanics deals with the microparticles, subatomic particles. If you take an electron here, suppose you cannot measure its position and momentum of the electron simultaneously with a 100% accuracy. That's what the meaning. So Heisenberg said that you cannot measure all the physical parameters simultaneously with the highest degree of accuracy. That is not possible. That's what the Heisenberg uncertainty principle says. Heisenberg uncertainty principle states that he said that there is an inherent uncertainty. It means it's already there within there is inherent, it is present inherently. There is inherent uncertainty in the act of measuring itself. That is, you are measuring the position of a particle means, however the measurement is confined, or however the measurement is involved, the precision, but whoever may be doing, there is inherent uncertainty in the measurement. Whoever does the measurement, the position or momentum, certainly there is some error always associated with it. This error, this uncertainty cannot be removed. That's the universal phenomenon. Okay. Here, whoever do the measurement, there is some error associated with it. There is always inherent uncertainty associated in the act of measuring a variable, whether it is a position or momentum. There is some error. It never be said it is completely correct or completely 100% right. It cannot be said so. This is a contrary to the classical physics. According to classical physics, whatever the measured values or quantities are assumed to be 100% correct. According to classical physics, whatever the measured quantities, the results were believed to be completely correct. It doesn't have the error associated. Something like that, it was the assumption. But according to quantum mechanics, whatever you measure, these measurable quantities, the measured quantities, certainly has some inherent, it's already present, it's there, inherent uncertainty associated. That is the difference between the classical physics and the quantum mechanics, quantum physics. Therefore, he made this was introduced in the year 1927. Heisenberg took a bold decision and he said there is a lower limit, whatever you measure, it got a lower limit of precision. Whatever the knowledge of the particle is known, I mean to say that Heisenberg took a bold decision, is said with 100% guarantee like that. There is the measurement certainly have a limit to the precision. It has got the error associated with it. It doesn't have the complete 100% correct like that. Okay. So you know that this is one of the most well-known Heisenberg uncertainty principle, that is the product of delta P, delta X greater than or equal to H by 4 pi. This is known to, this expression is known to almost all of them. Here you are measuring the two quantities. One is the position, X represents the position, P represents the momentum. So it is attached to the delta. It means the measured position X or the measured momentum P is not completely true. It is having an inherent error. It is associated to the inherent error. We are not taking it is a product of P and X. We are taking the product of delta P and delta X. Delta refers to the uncertainty, that is inherent error associated. See the measurement of if for example, if you take an electron, you are measuring the position of an electron, then measured value in their position is not completely certain. It is not completely certain. It is associated with an inherent uncertainty. It is associated with an error, that is delta x. Similarly, if you measure the momentum of the particle simultaneously, then there is an error, inherent uncertainty associated in its momentum. That's what the meaning. So if you take these two products, delta x and delta p, you will get, it is always mathematically can be shown that it is greater than or equal to h by 4 pi, where h is the Planck's constant divided by 4 times the pi. So imagine that delta x and delta p are inversely proportional. Delta x and delta p, they are inversely proportional. Whatever it is measured in the quantum mechanics, they are all the probable values. So you got the two probable values. One is probability in the finding the position of the particle, that is multiplied by the probability in the measurement of the momentum of the particle delta p. So if you take two such probabilities, you will get the probability square, p square. So this p square is quantum mechanically it is called the probability density. So the product will be the probabilities on the right side. So the value of delta x and delta p in this situation, you will get 1. It means that probabilities 1 means it's 100%. When you say 100%, it is certainty. It is certain. That's what. But it is not 1. It is greater than or equal to h by 4 pi. According to the physics, it is greater than or equal to h by 4 pi. It means that you cannot measure both the quantities. They are the conjugates now. Both the quantities simultaneously with the 100% precision. It is not possible. That's what the meaning. Okay. So now the product of two uncertainties delta x and delta p is minimum is equal to h by 4 pi and is always greater than h by 4 pi. Okay, this is Heisenberg's uncertainty principle, where delta x is the uncertainty, the measurement of position, and delta p is the uncertainty in the measurement of the momentum. When you take their product, it is always greater than or equal to h by 4 pi. Classical physics, the measurements of any parameter, physical parameter is accurate. It is discrete, definite value. But according to quantum mechanics, the measured values are not the exact one. They are always the probable values. They are probabilities. So according to Heisenberg's uncertainty principle, it states that in any simultaneous determination of the position and momentum of a particle, there always involves an uncertainty. There is always an inherent uncertainty involved in the measurement of the position and as well as the measurement of momentum. Take their products in their uncertainties, it is always greater than or equal to h by 4 pi. I told you if it is equal to 1 means the measured values are certain. It becomes mathematically, physically it becomes they will become certain values. Since it is greater than or equal to h by 4 pi, it is uncertain, not be measured. Certainly both of them simultaneously. That's what the meaning. And you also familiar with other uncertainty relations, that is delta E into delta T greater than or equal to h by 4 pi, where here E is the energy, T is the time. There is one more relation, delta L. L refers to the angular momentum, theta is the angular displacement. Their product in their uncertainties is greater than or equal to h by 4 pi. One of them is delta E into delta T greater than or equal to h by 4 pi, and other one delta L delta theta greater than or equal to h by 4 pi. These are also Heisenberg uncertainty principles along with the delta x and delta p greater than or equal to h by 4 pi. You may in the previous chapter, that is under lasers, so you know that there is a transition between two energy levels, 1 and 2. That is the photon absorbed energy is equal to the difference in E2 minus E1, and any photon that is released from the higher level to the lower energy level is nothing but again the difference of two energy levels E2 minus E1. that is delta E. You know that, isn't it? Delta E is the photon that is released. Okay. So when a particle is in the excited state, is going to stay a time in a lifetime of delta T. You know that it's 10 to the power minus 8 seconds. So if you take the product of the energy of the photon, the time it is spent in the higher energy level, there is always greater than or equal to h by 4 pi. That's what the meaning. Similarly, delta L is the angular momentum, the uncertainty in the measurement of the position, angular displacement. These are the three expressions of Heisenberg. Now we are going to come to the explanation to Heisenberg uncertainty principle. Look at these diagrams, three diagrams. They are called the wave packets. Say this is it's not a simple wave, a single wave. So this is due to this is the resultant wave of this is the resultant wave. There are many waves, 1, 2, 3, 4, 5, 6, etc. If you imagine there are many waves, their resultant looks to be like this way. Okay. So now and you got three similar diagrams with the first one is the longer one, second one is the little smaller, third one is little still smaller. So we call this as a wave packet. So now look at the green one. So now the waves upon superposition of many waves, due to superposition of many waves, we will see that this is the resultant wave. This is the resultant of many waves. Now you see that when you already learned from interference, when you see that it has got the nodes and antinodes. What are the nodes? Nodes are the points where you got the minimum amplitude, and the antinodes are the positions where you got the maximum height. When you say the particle is moving, when electron is moving, it is not simply associated with the single wave. It is the collection of waves. It's a wave packet. So within the wave packet, you see there is a peak in the wave, and there are nodes and antinodes. Antinodes represents the points of highest amplitude here. So the electron is moving this way. The electron is at the center of the wave packet. You have the probability of finding the particle is maximum at the center of the wave packet. At the center of the wave packet, you got the more probability of finding the electron or finding the particle. At the nodes, you have the lesser probabilities. It means the particle is confined more at the center of the wave packet. Okay. So in quantum mechanics, the particle is described by the wave packet. According to Born's interpretation, the particle may be present anywhere within the wave packet. See, since it is a wave, it is associated with the electron. So you have to say that electron is present throughout its wave. So now, since if you look at the amplitude of the wave at the center of the wave packet is more. Amplitude is more at the center. Therefore, you confine your observation at the center of the wave packet. It means that electron or the particle is more likely to be found at the center of the wave packet. That's what the meaning. So if the packet is smaller, this wave packet is smaller and smaller, then the amplitude at the center becomes narrower and narrower. So at the center you got the particle. You are more confined, you are moving towards the center of the packet. It means you are more, there is a probability, a higher probability of finding the particle at the center of the particle. Particle is confined, more confined at the center of the particle. It means that it is you are finding the particle at the center of the wave packet. When the packet is smaller, delta x is smaller. When the packet size is smaller, delta x will be smaller, and more you are more confined at the center of the packet. It means that you are there is more chances of finding the particle, more chances, more certainty in finding the particle. Since the packet becomes smaller and smaller, so inside you have the different waves. So you have many waves. Therefore, the d lambda is becomes, since the lambda there are more, it is associated with the de Broglie waves. Lambda becomes large, but the requirement is the d lambda should be smaller. It means that if there are no differences in the waves, in the two waves, it means they are the identical waves. Then it is easy to find its moment wavelength. If it is easy to find wavelength, means using this de Broglie wave equation, lambda equal to h by p or p is equal to h by lambda, then the d lambda is becomes smaller. It's tending to smaller. It means you can easily measure the wavelength. So h by d lambda tending to 0, the difference is smaller. Therefore, this h by d lambda, that is h by 0, means is kind of, mathematically speaking, it becomes infinity. Therefore, delta p tends to infinity. When delta x is smaller, it means you are trying to find the particle at the center of the particle. As the delta x, the wave packet is smaller and smaller, you are more precisely finding the position of the particle because it's confined at the center of the particle. But there is a problem in determining its momentum because lambda cannot be easily measurable. I mean, it is in the denominator. Therefore, there is a more uncertainty in measuring the momentum of the particle. If one of them is certain, other one will go more uncertain. That's what the meaning. If delta x smaller, so that you can identify the particle at the center of the wave packet more precisely, but the momentum becomes more uncertain. If you are able to measure the momentum of the particle, if the wave packet is large, if the delta x is large enough, if the delta x is large enough, then the waves are defined clearly. Then momentum becomes easy to be measured because it gives you the velocity. So the momentum becomes easier and delta x becomes large now. So delta x is large. It means the probability of finding the particle within the wave packet has increased. I mean, decreased because of its delta x value. So it is delta x is large. Probability of finding the particle is anywhere within delta x. Therefore, the position of particle is not easy now. It's not precise, but wavelength becomes more precise. So one of them will go more certain, and the other one will be less. So there is an inverse relationship between delta x and delta p. That is, one of them is certain. If the measurement, if the in the position of the particle is becomes more certain, then momentum becomes more uncertain. If the momentum becomes certain, then position of particle becomes more uncertain, like that. So there is an inverse relation between them. They are inversely connected. So now to get more precisely the mathematics, using mathematics, you can get the expression. You can remove this proportionality constant, that therefore delta x and delta p, that is greater than or equal to h by. So mathematically one can show that. So therefore delta p delta x is greater than or equal to h by 4 pi. That is the Heisenberg uncertainty principle. The conclusion now. What you did observe here, when the wave packet is large, velocity of the particle or the momentum may be fixed because of larger the width delta x. It is easy to measure the momentum and the velocity. But since delta x is increased, there is more uncertainty in finding the position of the particle because it is scattered anywhere between this larger value of delta x. As the delta x is larger, probability of finding the particle or the certainty of there is more uncertainty in finding the position of the particle, but more clarity in the wavelength and hence the momentum. That's because of its inverse nature. Therefore, it is impossible to know whether within the wave packet, where within the wave packet the particle is and what its exact momentum. It is not easy, I mean, it is not possible to know both of them accurately. Where exactly the particle is and what exact momentum it has, it is not possible. If you go by definition, Heisenberg uncertainty principle, according to the definition, in any simultaneous determination of position and momentum of the particle, the product of their corresponding uncertainties inherently present in the measurement is greater than or equal to h by 4 pi. It means in the measurement of position and momentum of the particle, the measured values are not exact. It is already associated with the some inherent error, that is delta x and delta p. Their product is greater than or equal to h by 4. It says that you cannot think of, according to the principle, you cannot think of the exact position or exact momentum for the particle, but you can think as it is their probabilities. You can think as the probabilities associated with finding the particle, and it is there are probable values for the momentum. The estimation of such probable values in quantum mechanics is done by using probability density functions. Application, one of the application is using Heisenberg uncertainty principle. We can show that the electron cannot be present inside the nucleus. So using uncertainty principle, I can show that electrons cannot be present inside the nucleus. See, the radioactive nuclei, radium or uranium, etc. Any radioactive nuclei that is, it emits alpha, beta, and gamma radiation, isn't it? A radioactive nuclei continuously emitting alpha particle, beta particle, gamma rays. Here, beta rays are equivalent to that of an electron. It means that you can say that electrons are coming from the nuclei, radioactive nuclei. It is not so. See, according to, from radioactivity, a radioactive nuclei that emits alpha particle, beta particle, and gamma radiations. You know that, isn't it? So where beta particles are equal to an electron. So then you can say that electrons are coming from the nucleus. It is not true. We'll explain this. See, if you apply the Heisenberg uncertainty principle, assuming that electrons are present inside the nucleus, you initially assume that electrons present inside the nucleus, then the size of the nucleus is of the order 10 to the power minus 14 meter. Then you can say that electron is somewhere present between 10 to the power minus 14, isn't it? The property of finding the particle with a nucleus is anywhere between 10 to the power minus 14. That is, electron can exist anywhere between this length 10 to the power minus 14. If delta x is 10 to the power minus 14, that is uncertainty in its position, you can measure the uncertainty in momentum. That is, you look at the expression delta p equal to h by 4 pi into delta x. If you take this, the value happens to be 5.2 into 10 to the power minus 21 kg meter per second. If that is the probable momentum of 5.2 and 10 to the minus 21 kg meter per second, then you can calculate the corresponding energies also. That is, delta E is equal to delta P into C. E equal to mc square. Therefore, Pc mc is equal to P into C. Therefore, it is Pc. E equal to Pc. Therefore, delta is equal to delta P into C. Use the delta P into this expression, 5.2 into 10 to minus 21 into the velocity of light, then it will be 9.75 MeV. So, the energy, corresponding energy will be 9.75 MeV. If you calculate the kinetic energy, that is P square by 2m, it will be approximately 85 million electron volts. So now the electron, if you assume that electrons are present within the nucleus, then the corresponding the kinetic energy of beta particle should be around 85 MeV. It means if the electrons are present inside the nucleus, whose kinetic energies will be approximately 85 MeV, million electron volts. But it is not possible. That is, experimental investigations have showed that the maximum kinetic energy associated with beta particles cannot be more than 4 MeV, cannot be more than 4 million electron volts. Now here, if you apply Heisenberg uncertainty principle saying that electrons are present inside the nucleus, then energies are around 85 MeV. But it is not so. Experimentally observed quantity tells you it cannot be more than 4 MeV. There is a large difference, a huge difference you cannot expect. Okay. Therefore, let us change our initial assumption that electrons cannot be present in the nucleus. If the electrons are present inside the nucleus, then corresponding energy will be 85 MeV. But it is not so. It is seen that it is only 4 MeV maximum. Therefore, we can say that electrons cannot be present inside the nucleus. The emission of beta particles are taking place during the transformation of neutron to proton. This was proved later on under nuclear physics. The emission of beta particles comes because of the transformation of neutron to proton. There is continuous transformations taking place, neutron to proton. During that process, this mass difference appears as a beta particle that is released, but actually electrons do not stay inside the nucleus. So we have come to the almost end of the session. Particles delta x delta p greater than or equal to h by 4 pi, that's the limit. There is an inverse relationship between delta x and delta p. Delta x is inversely proportional to delta p. The measured values are nothing but the probabilities. They are whatever you measure under these quantum mechanics, the delta x delta p, they are only the probabilities, they are not the exact values. And using Heisenberg uncertainty principle, we have predicted, we have showed that electrons cannot be present inside the nucleus. Okay.